Hello everyone, I will talk about hybrid stars with fermionic dark matter core. Some observational data from cosmology and astrophysics strongly suggest that the non-relativistic matter component of the universe is dominated by dark matter. The nature of dark matter is still an open question. It is fermionic or a bosonic matter. New constraint from Atlas CERN impose for fermionic dark matter a mass greater than 500 GeV, in this way excluding the light dark matter candidates. Kaplan et al. Found constraints on neutron star radi by combining multi-messenger observations of the binary neutron star merger, this one, with nuclear theory that best accounts for density-dependent uncertainties in the equation of state. And it was found that the radius 1.4 stellar masses are equal to 11 kilometers with these uncertainties. And the NICER collaboration measured simultaneously the mass and the radius of this pulsar. And two different analysis groups found independently that this pulsar has a mass of 1.44 stellar mass with a radius of 13.02 kilometers. And another group found a mass with 1.34 stellar mass with a radius of 12.71 kilometers. And in the same year, Cromarty et al. Measured the mass of a neutron star in a binary system with a white dwarf. This reference, and they found that mass of this neutron star, it's 2.14 stellar masses. And here in this talk, we want to answer this question. Is it possible a hybrid star and a neutron star with and without dark matter fulfill the current constraints? This is our main question in this talk, right? And for constructing the hybrid EoS, we used three equations of state for the hadron phase. For the crust, we use the PPS and NV. And for higher density, we use the parametrization NL3. Okay, and for the quark phase, we use the VMIT model. And in this model, it is included the vector interactions, and included the vector interactions. This model is capable of reaching 2 solar masses. And for the dark matter, we consider dark matter it's a fermion with 500 GeV, right? Since the lower masses were ruled out by the actual Atlas CERN measurements. And here are the reference. And we are considering both cases, both EoS having a temperature equal to 0, and they are in beta equilibrium conditions. And for the phase transition, we choose the maximum construction, since it's one of the simplest way to construct a phase transition. This construction has a local charge conservation, and it's given by these conditions, right? When we plot the two equations of states for pressure and chemical potential, and when they intercept each other, we found the critical pressure and the critical chemical potential, right? And this critical pressure will give us the pressure where the phase transition occurs. Here are the Lagrange density for this parametrization, right? Where here are the psi contains the nucleons with a mass m, sigma, omega, and rho mesons. We have the electromagnetic field and the non-linear self-interactions of the sigma field. That is here, right? And here we have the nuclei parameters, right? And here are the reasons to use this parametrization. It's able to give a quantitative description of the ground state properties of spherical endoformed nuclei at and away from the stability line. It is in an excellent agreement with experimental nuclear masses. It reproduces the isoscalar monopole energy in a rather different regions of the periodic table, such as lead and zirconium nuclei. Here it's the model for the quark phase. We can see here for the energy density, the bag constant, the kinetic term for the fermions, for the quark UDES, the interaction term, right? And the kinetic energy for the electron and mole. If we remove this term and this term from chemical, these terms, right? From the chemical, from these equations, we recover the standard MIT model. Here are the parameter, here are the values used in this equation of state, right? With this interaction term. We should mention that the bag constant value softens the EoS, while the interaction term stiffens the EoS, right? So when we are constructing the hybrid star, we have this balance between these two terms to be fulfilled with these conditions. And for the asymmetric fermion dark matter, we choose this simple one. Here it's the kinetic term for the fermion. And we just include now a self-interaction potential here, where G is the dark matter mediator coupling constant and Ma the mediator mass. For simplicity, we adopted these values as 1 and consider the mediator mass to have 100 eMV. And as we mentioned before, our dark matter will have 500 GeV. And we can ask ourselves how this dark matter is captured by the core. Well, when the compact object passes through a dark matter, it can capture dark matter particle from it. We can see in this representative way when the compact object is forming and it is passing through this dark halo, it can capture the dark matter from here. And this dark matter loses energy due to its interaction with the high baryon density inside the compact object. The gravitational force trapped the dark matter inside the compact object. And this dark matter inside the compact object will depend on the evolution history. For example, if the galaxy will not have this dark matter halo, it will not possible to capture it. And some recent observation suggests that some galaxies are deficient in dark matter, and we can see in this archive, right? And we consider that the average number density of nuclear times is 1,000 times larger than the average dark matter density. Considering nuclear saturation density equal to 0.16, we have a dark matter density equal this one, which gives us a Fermi moment of dark matter equal to about 0.033 GeV. This will vary this value to fulfill the constraints mentioned in the introduction. All right, and here are our results, our EoS and the speed of sound in the median for the three equation of states. Here in the dot line, red dot line, we have the NL3 equation of state, right? And when we include the dark matter, here we have 500 GeV with this Fermi moment. It's more stiffer. It's more softer than this one, right? And the same can be seen in the hybrid stars when we include the hybrid EoS. When we include the dark matter softens the EoS, right? And why we plot the speed of sound? Because this is one of the requirement to have a casual EoS, and these gaps represents the phase transition, right? And another thing that we should mention, it's that in this paper was suggested that the phase transition must be greater than the 2 times saturation density. So these two EoS satisfies this condition. And here are our results for hybrid stars with and without dark matter. Without dark matter, we have this the green line and the red line, right? Both crosses the orange constraint from Miller and reach this pulsar. When we include dark matter, it shifts to the left, the two curves to the left. But now selecting this parameter, the Fermi momentum of dark matter, for dark matter with 500 GeV, we see that the both EoS passes through these constraints and also satisfies the maximum mass. Here are the results from alpha plus the m, and they consider here a bosonic dark matter, but it shifts to the left very little compared to our results, right? And for the nuclear case, we have more results from the literature. Valeca 1 and Valeca 2 plus dark matter are from the literature. We have the green line for Valeca 1 without dark matter. Black line considering a dark matter of 200 GeV with this Fermi momentum. Here we can see that the shift from the green line to the left is bigger than the previous case, and it's bigger here also, right? Using Valeca 2, that it's with this parametrization NLO3, the Valeca 2 used the NLO3 parametrization, we can see that the curve is almost equal in the maximum mass, but in this region, the two curves are different because we use it two crusts while they don't. And in the red line, Valeca 2 is without dark matter. When they include dark matter, it goes to the cyan line, right here. But they are considered both both Valeca are considering 200 GeV, and we consider here 500 GeV with a different Fermi wave number, right? And our results for 500 GeV, it's the yellow line, which passes through these constraints and also satisfy the pulsar mass, this maximum mass. And this is a recent observation, recent gravitational wave observation that can be a neutron star or the lightest black hole, right? That's why I put this band here. And finally, we choose it to calculate for 200 GeV, and for the same Fermi momentum has Valeca 2 to compare the results, since the only difference here are how we incorporate dark matter in our equations of state, right? Comparing these two results, we have the cyan magenta line here and cyan line. We can see that they are almost the same for the maximum mass. In this way, we can conclude that even for our approximation, that's very simplistic one, our results are still in agreement with a more elegant implementation of dark matter. And here are the conclusions. Some of them I already told you, right? And I won't talk about this one. That the result from Valeca 2 also satisfy this pulsar and the nicer constraints, but for a different wave number, right? And our next work will will be check if the EoS presented here, the hybrid EoS, satisfies the tidal deformability parameters of this gravitational wave observation, right? And here are the references. And I would like to thank you, my PhD advisor, Professor Caesar, and the Brazilian agency funding, CNPq, for their financial support.